Hey, science enthusiasts! Today, we're diving into one of the most controversial and mind-bending topics in modern astrophysics. What if there's no dark matter, and our understanding of gravity is completely wrong? For decades, dark matter has been used to explain the universe's invisible mass. But what if it's all a mistake? Could our theories about gravity be broken? Stay tuned as we explore this cosmic puzzle and what it could mean for our understanding of the universe. Astronomers have just made a groundbreaking discovery that could upend everything we thought we knew about the universe. They've found compelling evidence that challenges the very existence of dark matter, hinting that our current understanding of the cosmos might be in for a major overhaul. By carefully studying the rotation curves of galaxies, how stars move at different distances from their galactic centers, scientists discovered that the mysterious dark matter, long thought necessary to explain these motions, might not be needed after all. This stunning revelation adds fuel to the growing skepticism around dark matter, a substance believed to make up 27% of the observable universe. For nearly 90 years, dark matter has been a cornerstone of cosmology, and despite billions of dollars spent on research, countless surveys, and elaborate theories, we still have no idea what it truly is. But now, some physicists are beginning to ask a bold question: does dark matter even exist? Or is the real issue a deeper misunderstanding of gravity itself? So, what exactly did astronomers find that's shaking up the dark matter debate? And how does this discovery point to potential flaws in our understanding of gravity and the universe's fundamental structure? Get ready, because this could change everything we know about the cosmos. But here's the big question: if dark matter doesn't exist, then what explains decades of observations we've made in the cosmos? This new study delves deep into the very roots of the dark matter theory, challenging the very first evidence that supported it, specifically the rotation curves. Let's travel back to 1933, when Swiss astronomer Fritz Zwicky made a startling discovery in the Coma cluster, a massive collection of about 1,000 galaxies located around 320 million light-years away. Zwicky noticed something odd. The galaxies on the outer edges were moving much faster than expected. When he compared the cluster's rotation speed with the estimated visible matter, he found something astonishing. The cluster was spinning so quickly that it should have torn itself apart. Yet, it remained intact. Zwicky deduced that there had to be something else at play, an invisible force with mass exerting a gravitational pull strong enough to keep the galaxies bound together. He named this mysterious substance dark matter because it neither emits, absorbs, nor reflects light, making it completely invisible to our telescopes. While many theories have since emerged, the implications of this new study could reshape our understanding of the cosmos. What does this mean for the decades of observations we've made? And could we be on the brink of a major breakthrough in how we perceive the universe? Stay tuned as we explore these exciting developments. Astrophysics and cosmology were born from the innovative mind of Fritz Zwicky, a brilliant yet controversial figure known for his bold and sometimes outlandish ideas. Back in Zwicky's day, cosmology was still in its infancy, and it was common in scientific circles to joke that there was speculation, then more speculation, and finally cosmology. While some of Zwicky's theories sparked interest, many were often left unexplored. This pattern also applies to dark matter. It wasn't just a year or two after Zwicky proposed his hypothesis. It took a solid 40 years for the concept of dark matter to gain traction. It wasn't until the 1970s that American astronomer Vera Rubin stepped onto the scene, providing king of the universe. However, Vera Rubin and her colleague Kent Ford made a startling discovery: galaxies didn't follow the expected rotation pattern. When they studied the rotation curves of spiral galaxies, starting with our neighboring Andromeda galaxy, they found that stars were zipping around at unexpectedly high speeds, even as their distance from the center increased. According to the laws of gravity, stars farther from the center of a galaxy should move more slowly. But what Rubin and Ford observed was revolutionary. Stars far from the center were moving just as quickly as those closer in. The visible matter in these galaxies simply couldn't account for the incredible rotational speeds of the stars. This revelation suggested that there was something more lurking within these galaxies, something invisible. In the following decades, evidence in favor of dark matter continued to mount. In the 1980, astronomers observed gravitational lensing in galaxy clusters, where the light from distant objects is bent by the immense gravity of massive galaxy clusters. This phenomenon provided compelling further evidence for the existence of dark matter. Then, in the 1990s, measurements of the cosmic microwave background, the afterglow of the Big Bang, and the large-scale structure of the universe painted an even clearer picture. With each new discovery, it became increasingly apparent that dark matter was a crucial piece of the cosmic puzzle. Get ready to uncover how these groundbreaking findings transformed our understanding of the universe. The universe is far more clumpy and filamentous than it would be if it were composed solely of visible matter. Even computer simulations reveal that dark matter is a critical ingredient. Without it, the large-scale structures we observe today simply wouldn't exist. In this way, dark matter has become a deeply rooted concept in our most successful cosmological model, known as the lambda cold dark matter model. But even as evidence piled up in favor of dark matter, one major question loomed: what exactly is it made of? We knew something mysterious was exerting a gravitational influence on its surroundings, but we had no idea what it was. Interestingly, our theories of gravity weren't the first things we examined. Initially, neutrinos emerged as potential candidates for dark matter. These tiny, electrically neutral particles interact weakly with other matter, which matched the expected properties of dark matter. In the 1990s, experiments even suggested that neutrinos had small but non-zero masses, indicating they could contribute to the universe's total matter density. However, it wasn't long before we realized that neutrinos were unsuitable. Their low mass and high velocities meant they traveled close to the speed of light, giving them the characteristics of hot dark matter. This type of matter isn't capable of forming the dense galaxy structures that cold dark matter can. As a result, the idea of neutrinos as dark matter candidates was set aside. The search for the true nature of dark matter continues, and each new discovery brings us one step closer to understanding the universe's most elusive secrets. Once neutrinos were ruled out as the primary component of dark matter, astronomers turned their attention to a new set of potential candidates: massive compact halo objects, or MACHOs. These intriguing entities include brown dwarfs, neutron stars, and black holes objects that are notoriously difficult to detect because they emit little or no light. Initially, scientists were hopeful that these MACHOs could account for the unseen mass attributed to dark matter. However, further analysis revealed a significant shortcoming. The total mass contributed by MACHOs was insufficient to explain the gravitational effects of dark matter observed in galaxies. Despite their mysterious nature, MACHOs couldn't fill the gap, leading to their dismissal as the primary players in the dark matter saga. Next, attention turned to primordial black holes formed from density fluctuations in the early universe. If these black holes had sufficient mass, they would have been stable and would not have evaporated due to Hawking radiation, making them viable dark matter candidates. But there was a catch: no primordial black holes have ever been discovered. This lack of evidence ultimately ruled them out as a major component of dark matter. As researchers continued their quest to uncover the true nature of dark matter, it became clear that the search was far from over. Each hypothesis brought new excitement and challenges, pushing scientists to dig deeper into the mysteries of the cosmos. As the search for dark matter continued, attention turned to two intriguing candidates: weakly interacting massive particles, WIMPs, and sterile neutrinos. However, despite extensive efforts, there's been no experimental evidence supporting their existence. After years of failing to detect any dark matter particles, even in the world's largest particle colliders, some physicists began to question whether dark matter is real at all. This skepticism led them to explore alternative theories of gravity. One of the most fascinating alternatives is called modified Newtonian dynamics, or MOND. Instead of assuming there's extra unseen mass at play, MOND proposes that the laws of gravity themselves change at very low accelerations, like those found far from the centers of galaxies. In a galaxy, the gravitational pull experienced by a star is determined by the total mass contained within its orbit. According to Newtonian dynamics, if you plot the speed of stars against their distance from the galaxy's center, you'd expect the rotation curve to drop off at larger distances, as gravitational force weakens the farther you go from the center. Yet, surprisingly, many galaxies display rotation curves that remain remarkably flat, even at vast distances. This is where MOND steps in. It explains the flatness of these curves without the need for dark matter. In the outer regions of galaxies, where acceleration is very low, MOND's modified equation takes over, meaning that gravity doesn't diminish as quickly as traditional Newtonian physics would suggest. As a result, stars maintain higher speeds than we'd expect, perfectly matching the observed flat rotation curves. One key aspect of galaxy dynamics that could help distinguish between MOND and the standard cosmological model, known as the lambda cold dark matter (LCDM) model, lies in the unique behaviors of these galaxies. Stay tuned as we unravel more about this fascinating cosmic debate. To truly understand the behavior of galaxy rotation curves at great distances from the galactic center, astronomers are focusing on how these curves behave in the outskirts of galaxies. In the lambda cold dark matter (LCDM) model, dark matter halos are responsible for preventing the rotation curves from declining as Newtonian physics would predict. These halos typically have a finite radius, ranging from a few kiloparsecs to about 200 kiloparsecs. But what happens beyond this range? As the influence of gravity wanes, one would expect the rotation curve to start to decline beyond the radius of the dark matter halo. However, MOND predicts the opposite. In the far reaches of the galaxy, where stars and gas experience extremely low acceleration, MOND's modified equations take over, suggesting that rotation curves should remain flat even as we move beyond the expected extent of the dark matter halo. To determine whether MOND or the LCDM model provides a better explanation of galaxy dynamics, astronomers have analyzed rotation curves extending into the range of megaparsecs. They studied isolated galaxies using data from the Kilo Degree Survey Data Release 4, aiming to unravel the mysteries of galaxy behavior and ultimately figure out which model better describes our universe. Researchers are diving deep into the large-scale structure of the universe by examining the fascinating effects of gravitational lensing. They split galaxies into 4 groups based on their mass and compared 2 distinct types: early type, older galaxies, and late type, younger galaxies, all within similar mass ranges. To predict how these galaxies should behave, they used the Navarro-Frank-White density profile for the lambda cold dark matter (LCDM) model. According to this model, star speeds should decrease at the outer edges of galaxies because dark matter halos become less dense farther out. However, when the researchers analyzed the data, they discovered something surprising. Instead of slowing down, stars maintained a consistent speed even at the farthest reaches of the galaxies. This intriguing pattern was evident across all mass groups for both early type and late type galaxies. These unexpected results cast doubt on our current understanding of dark matter, suggesting that our theories may be incorrect or incomplete. Conversely, this data aligns perfectly with the predictions of modified Newtonian dynamics, MOND, which expects galaxy rotation curves to remain flat in low acceleration environments. The consistency of these findings with MOND's predictions opens up exciting new possibilities for understanding galaxy dynamics and challenges us to rethink the very nature of dark matter. Stay tuned as we continue to uncover the secrets of the universe. This discovery marks a significant win for modified Newtonian dynamics, MOND, and presents a challenge to the lambda cold dark matter, LCDM paradigm. While several studies lend support to MOND, one of its most remarkable successes lies in its prediction of massive young galaxies. Since 2022, the James Webb Space Telescope has been capturing images of enormous early galaxies that seem to defy the standard cosmological model, which includes dark matter. According to the LCDM model, galaxy formation involving dark matter should be a gradual process, making it unlikely for fully grown, massive galaxies to exist so early in the universe's timeline. However, the rapid emergence of these colossal galaxies aligns much more closely with MOND's predictions, suggesting that galaxies could form much earlier than previously thought. Despite its strengths, MOND is not a complete cosmological theory and faces significant challenges. It lacks a relativistic framework and struggles to explain the observed mass discrepancies in galaxy clusters. Additionally, there are inconsistencies between some of its predictions and actual observations. These limitations have kept MOND from being widely accepted as the standard model of cosmology. As the debate continues, we stand at a fascinating crossroads in our understanding of the universe. Will MOND's intriguing predictions reshape our cosmic narrative, or will the LCDM model hold its ground? Only time will tell. Right now, MOND and LCDM are engaged in a fascinating tug of war, each offering insights into some of the universe's most perplexing phenomena, yet each falling short in different ways. Picture trying to understand the movement of stars in a galaxy billions of light years away. Both models provide theories, but how do you truly grasp the complexities of such movements? That's where Brilliant comes in. This revolutionary platform transforms the way we learn about complex topics. Rather than just passively consuming information, Brilliant allows you to actively engage with each lesson through hands-on problem solving, which has been proven to be 6 times more effective than traditional video learning. The lessons are designed by experts from renowned institutions like MIT Duke and Caltech, as well as leading tech companies like Microsoft and Google. With Brilliant, you can cultivate critical thinking skills that extend beyond mere memorization of facts. The best part? It seamlessly fits into your daily routine. In just a few minutes a day, you can turn idle scrolling into powerful opportunities for personal growth. I've personally found their scientific thinking course to be especially engaging. It's like tackling real-world challenges in physics, from collisions to complex motion scenarios. So why not dive in and elevate your understanding of the universe today with Brilliant? Your journey into the cosmos starts here. To predict how these galaxies should behave, they used the Navarro-Frank-White density profile for the lambda cold dark matter, LCDM model. According to this model, star speeds should decrease at the outer edges of galaxies because dark matter halos become less dense farther out. However, when the researchers analyzed the data, they discovered something surprising. Instead of slowing down, stars maintained a consistent speed even at the farthest reaches of the galaxies. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.